Hello and welcome to lecture number 6 in organic chemistry. Today we're going to be talking about organic chemical reactions, and there's 4 or 5 you're responsible for. The first of these is perhaps the most familiar, the combustion reaction. Combustion is a rapid chemical reaction between a hydrocarbon and oxygen, and it typically produces carbon dioxide and water vapor. That's if we're talking about a complete combustion. There's also a tremendous amount of energy in the form of thermal energy and light that's produced. Incomplete combustion, it gives rise to toxic end products such as carbon monoxide and solid carbon. The typical combustion gives rise to a combination of these end products, and I'll show you that in a minute. The combustion of octane looks like this chemically. 2 octane molecules would react with 25 oxygen molecules to generate 16 carbon dioxide and 18 water vapors, plus a great deal of energy. And this water vapor piece is something the province is very highly invested in. They want you to understand that when combustion of hydrocarbons take place, the water comes off as a vapor for their own reasons. Incomplete combustion looks like this and like this. So in this second chemical reaction, you'll notice there's very much less oxygen present. So the system is oxygen starved, so rather than generating carbon dioxide, we see carbon monoxide generated. It has a very different chemistry than does carbon dioxide. Carbon monoxide is lethal. It will bind to your hemoglobin and never release, which is why it's extremely dangerous to run your automobile in a closed space. Because your automobile does not burn clean, it generates a great deal of carbon monoxide, which can be fatal. If you're very oxygen starved, oxygen depleted, you're going to get this third end product. You're going to get solid carbon or black soot. You see it on barbecues and on burned toast. It's a mild toxin. Just a cautionary tale, no combustion is 100% complete, and typically all 3 of these reactions occur at the same time. So you get a combination of these end products being produced. For this reason, never run a camp stove or a heater in an enclosed space because you're poisoning yourself. Addition is another organic reaction. Addition reactions take place between unsaturated hydrocarbons. So these are the alkenes and the alkynes. And we're reacting with them with small diatomic molecules such as hydrogen or a halogen, like F2 or Cl2. A catalyst usually accelerates the reaction, but it's already pretty rapid. The end products are more stable than the reactants, and that favors a rapid reaction. Both atoms from the diatomic molecule are added across the double or the triple bond, and as a result, there's no secondary end product. Here we see a reaction between ethine, C2H2, and liquid bromine, Br2. And the bromine gets added across the triple bond and opening up one of the 3 bonds, giving rise to an alkene, 1,2-dibromoethene. If we continue to add more bromine, you'll see we'll add another diatom, another Br2, across the double bond and to generate a single bond. 1,1,2,2 tetrabromoethane. So these 2 reactions are in series. Both are rapid and both are catalyzed. Substitution reactions are very much slower than addition reactions. Typically, saturated hydrocarbons, the alkanes, go through substitution reactions. The benzene ring, it looks like it's unsaturated, but it reacts like it is saturated. Benzene typically goes through a substitution reaction rather than an addition reaction. The second reactant in this system is typically a small diatomic halogen molecule, such as F2 or Cl2. What happens is a hydrogen atom on the hydrocarbon is replaced by a halogen atom. A secondary product is always present. It's always the result of the hydrogen coming off the hydrocarbon, bonding to the second halogen atom. These reactions are very slow. Quite often light will catalyze them, but they continue to be quite slow, certainly slower than addition reactions. Also, there's often more than one end product. but one is produced in greater quantity than the other. And I'll show you that here in the substitution between propane and bromine. So here's our propane, C3H8, and you'll see there's two molecules. So we're going to look at two substitutions. Here we've got our Br2 molecule. One of the atoms bonds to the middle carbon on the propane, and in fact it substitutes for one of the hydrogens, and the hydrogen bonds to the remaining bromine, and it gives us our secondary end product, HBr. The resulting alkyl halide then is 2-bromopropane. However, there's a second propane molecule and a second Br2 molecule. That Br2 molecule substitutes with a hydrogen on the first carbon in the propane, and that gives rise to 1-bromopropane. And of course the hydrogen that comes off bonds with the remaining bromine to give us a second HBr molecule. So there are two alkyl halides produced, but they're not produced in equal quantities. In fact, one is greatly favored over the other, typically sort of 99% to 1%, although those percentages vary. Here's another substitution reaction, except it's with a benzene ring. So here we have C6H6 reacting with Cl2. One of the hydrogens comes off and is substituted by one of the chlorine atoms. And that hydrogen that's been removed bonds with the other chlorine atom to produce hydrogen chloride. And we're left with our chlorobenzene as the desired end product. Elimination reactions. Elimination reactions involve the removal of atoms from a hydrocarbon, which are then replaced with unsaturated bonds. So if we have a need for ethene or another alkene, which are used for industrial processes, we can generate them by reacting an alcohol in a highly acidic sulfuric acid solution. So this is an organic alcohol in an inorganic acidic solution. And the acid is simply acting as a catalyst. The acid is not a reactant. What happens is water is eliminated from the alcohol and we're left with an alkene. Similarly, with an alkyl halide, we react it with a strong base. So in this system, the base is a reactant. It's not a catalyst. And again, water is eliminated and the halogen comes off as a free ion. Ethene is produced through both of these processes. So let's look at the first one, elimination of water from ethanol. So here's our ethanol, and in a very strong sulfuric acid solution, we eliminate water, and a double bond is formed between the two carbons. So we get our ethene. The second reaction is the elimination of hydrogen from chlorine. I think I said water is eliminated, but in fact hydrogen is eliminated. And it's eliminated by reacting with, not in the presence of, but with a strong base. So this base is not a catalyst, it's a reactant. It strips off a hydrogen to form water, and the chloride ion comes off as a free ion as well. And of course there's our desired end product, there's the ethene. So these are the two elimination reactions you're responsible for. There's a further elimination reaction we look at, and it's called esterification. Esterification is the formation of an ester from an organic alcohol reacting with an organic acid. So this is not what we just looked at. Here we're talking about organic alcohol reacting with organic acid, and they're reactants. And water is eliminated, and an ester is produced. These typically strong inorganic acid is also present as a catalyst, and heat drives these reactions as well. So we're going to look at the esterification between ethanol and methanoic acid. On the left here we've got our ethanol, on the right we've got our methanoic acid. Water is eliminated, so this H and this OH come off as a secondary end product, water, and an ester linkage is formed between the alcohol and the acid. Ethanol, of course, the alcohol forms the prefix of the name of the ester. Ethanol becomes ethyl. And the acid forms the root of the ester's name. Methanoic acid becomes methanoate. So our ester in this case is ethyl methanoate. That's the end of the questions. I've got the end of the lecture. I've got a few questions for you to consider. Question 1. Octane reacts with oxygen to produce carbon dioxide and water vapor. This is an example of, hopefully you recall, this is the classic pattern for a combustion reaction. C. Which of the following statements is true? Alkanes go through addition reactions. Well, no, hopefully you recall that alkanes go through substitution reactions. So A is out. Alkenes go through addition reactions. That's true. But are they slow? No, they're quite rapid, so B is out. Alkanes go through substitution reactions, yes, which are slow and give rise to secondary end products. Yes, that's a true statement. The answer is C. Although let's check D just to be sure. Alkenes go through substitution reactions. No, they sure don't. The answer here is C. Which of the following statements is true? The benzene ring structure is highly stable. Well, yes, it is. So benzene typically goes through an addition reaction. No, not true. B, the benzene ring structure is highly unstable. Not true. C, the benzene ring structure is highly stable, so benzene typically goes through a substitution reaction, and that's in fact the correct answer. The answer here is C. Let's check D. The benzene ring structure is highly unstable. No, not true. So again, the answer is C. What is the name of the ester produced by the following reaction? Okay. So you see there's an alcohol here with 1, 2, 3 carbons. So this is propan-1-ol. Reacting with 1, 2, 3, 4, reacting with butanoic acid. Water is eliminated, and an ester linkage is formed. So here's our ester. So, of course, the alcohol forms the prefix of the name, and propan-1-ol becomes propyl. So choice A and choice C are out. Butanoic acid forms the root of the ester's name, 1, 2, 3, 4. Butanoic acid becomes butanoate. So this is in fact propyl butanoate, and the answer here is B. That's the end of the lecture. Hopefully you found it of some value. We'll see you next time when we talk about polymers.